Hello. My name is Kyle. I'm the DevRel at Fhenix. And our goal is to build on-chain composable private contracts using Solidity. So what is Fhenix? Fhenix is basically an L2 project that, again, is trying to leverage composable on-chain encryption. So obviously privacy in the smart contract space is very popular. Primarily, most of the attention is being given to proofs using projects using zero-knowledge proofs. In some ways, there's kind of some limitations in the sense where like maybe ZK isn't the end game specifically for composable on-chain privacy. Specifically in the sense where FHE allows you to run operations over ciphertext. Which kind of allows you to create an on-chain state so you can have more complex logic versus just point of attestation privacy, which scales a little bit differently. So if you want to get started with the private order flow example, here's a QR code to a sample repo. We also will have a lot of other aspects of the presentation to add to. But here's a quick contract import example. So one of the benefits of building on Fhenix is that you don't have to go and learn another language. We're trying to prioritize the developer experience in the sense where it should be as simple as considering that an integer would be an encrypted integer. So here we have kind of an example where the FHE is just import on the top of the contract. Here are some examples of how you could pass in ciphertext. And a ciphertext, for those of you not familiar, it's essentially sort of like, think of it like a hash value that kind of represents the knowledge of the plain text as well as noise. FHE is using kind of a noisy encryption here. And as you can see on line 11, we will move towards a type of a decrypt, which will kind of, that's essentially what is exposing the value to the rest of the network. So here's an example of a local setup if anybody also would like to use a traditional, like a hard hat repo. So this can be run locally through the plugin. There's other opportunities to build your contract out this way, using different testing that's possible. So feel free to fork it and give it a shot. We also have a remix plugin that will help you generate and format the ciphertexts so you can actually pass them as input params for your contract, as well as handle permissions in the sense of basically who can view what data. We'll get a little bit more to that later, but if you have any questions about any of the slides, we do have the link to the documentation for each corresponding part of the presentation. So here's an example of how you put an input into a function. Traditionally, you would probably just pass this in as an integer or a uint, I guess, of size 8, for example. However, different formatting is necessary in order to pass in the ciphertext. And we do try to set up tools to make it as easy as possible for developers to pass this in. But essentially, you can think of this as just a level of obfuscation on-chain. So instead of having to off-chain certain aggregation or security when it comes to MEV or basically anything, you can use FHE in this sense. And so if you see here, there's actually 2 different ways to save to this encrypted integer 8 of 8-bit length. So it could either be arbitrary bytecode, for example, if you want to develop using for example, if it needs to be get passed in from the call from another function, or if you just directly want to call it in terms of the ciphertext here. OK, so conditional logic also does apply a little bit differently when you're trying to advance the state over an encrypted field, because it's not as deterministic as like natural blockchain execution, because what the state could branch to is dependent on a value that isn't known. So this does have some issues when it comes to like gas estimation, but again, this is filled through in terms of like just kind of estimating as an arbitrary sort of block of bytecode, if that makes sense. So as you can see here, the first example is kind of something that would be more natural to any of us that have really run like kind of simple if-then logic. However, having to apply this logic like the conditional case over something that's encrypted, again, has kind of the issues I was talking about earlier. So the bottom is basically kind of using a selector method, which is kind of like a multiplexer in the sense where it takes in a Boolean value of is higher here, and then we'll slot either the value or the existing bid and set that to the corresponding, wherever it needs to be. In this case, it's a specific mapping. And we'll kind of get to why this mapping is important later. But it's good to keep in mind of, specifically if you want to check if a value is less than and then apply conditional logic, you would use some sort of a selector here and then branch based off of the encrypted integer. It could be a Boolean, could be an encrypted Boolean. And require statements. So require statements are also different in the sense that sometimes you don't want the contract to execute if a certain threshold is or isn't met. Traditionally, this is a relatively simpler thing to calculate, and oftentimes you can do it before the contract even needs to be run. However, obviously with FHE, especially when it comes to multi-party, a lot of this information isn't going to be known. So require statements also need to be a little bit different. Another thing to be cognizant of is what information does leak. Because at the end of the day, if you're trying to build a really secure encrypted application, one of the things that, one of the core design principles is information leakage, because that can take down entire systems. But the FHE require here is sort of like an example of a condition of what's not going to make this contract work. So if you have a Boolean condition, for example, and you can look at how the contract executed, you would be able to tell if the contract got reverted or not without necessarily seeing the contents. So to go on a little bit more about conversion leakage. So from a high level, I like to think of it in the sense where, like, if it happened at some point, there's a trail of it, right? Because in general engineering principles, right, everything's sort of deterministic. That's how we can build forward and expand on top of things. Some would say stand on the shoulder of giants, I suppose. But when it comes to information leakage, by ever exposing an unencrypted integer here, so a standard uint256, to try to convert that to something like a uint32 or uint256 for that matter, that conversion is going to have some issues because the plain text value that it ever existed will have leaked. So the safest way of encrypting your data this way is to make sure that it's formatted as a ciphertext. And like I said, we believe that this is kind of an extension of sort of an application use of zero-knowledge technology, zero-knowledge proof technology. Like under the hood, part of our operating system, we actually do use zero-knowledge proofs of plain text knowledge to verify that the developer or that the participant knows that the ciphertext was constructed correctly and that the contents, the plain text contents are known so that logic can be applied and a certain level of construction trust can be built in towards the application moving forward. Okay, so what is FHEOS? So we have heard, I've kind of gone on about how to build with Fhenix, but from a high level, what Fhenix is working on is we are building an encrypted L2, but also we are working on the general ecosystem around what's going on in the FHE space. For example, we have use of the threshold network, which is kind of like if you think about it in terms of multi-party compute and the threshold encryption, this is kind of what some of the FHE oracles that eventually are going to be read for necessary decryption. But basically, the FHEOS library specifically is kind of a wrapper around Zama's TFHERS library, which is a Rust library that's, again, maintained by Zama and uses a specific FHE encryption scheme to handle certain operations. And from there, we try to keep our stack as modular as possible, even in the sense where, there's a lot of trendy stuff about, atomic execution, fragmented liquidity, et cetera. So one of the aspects of keeping this modular is that we could attach it to, different WASM execution environments. In this case, like we're using the test environment is using the Arbitrum 4 prover, the Nitro prover, for the integration for stylus so that we can actually run the TFHERS functions, I guess you could say the solidity endpoints, import them as like stateful precompiles. And so, again, this could be applied to different stacks as it's getting more and more popular. Right now, we can convert to networks run using the GoEth client. But from a high level, this is kind of what we're doing. Like I said, under the hood, if you dig into the TFHERS library, it is using ZK POK for the construction of the plaintext and knowledge of the plaintext. And the threshold service network, will apply a lot of the security that can be used between, different networks that eventually get added to. So It's kind of interesting because it kind of comes down to like how do you give encryption as a service? I suppose there's some trains of thought, like some people might advocate for using some sort of bridging, but then you're bridging a ciphertext. Ciphertext value is still relatively large. They could be as large as like 8 kilobytes. Trying to send that through some sort of bridge obviously is going to have its own issues. You could try to segregate it, the message. However, there I think also is an argument for just applying the stateful precompiles directly to the client itself, and then they can connect to each other using the threshold service network, which is sort of kind of like the shared state of kind of like leveraging the network effects for encryption and just general security. So what is Fhenix.js? Fhenix.js is a library that you can import into the client, and it'll help you kind of earlier where I was going over ciphertext formation, and when it comes to permission viewing, basically who has access to this data. This is a way to integrate it into JavaScript, however developers want to build on the front end, and basically it just kind of helps you integrate with the ABI a little bit easier, just in the case of formatting. So again, hopefully the developer experience, we're trying to make the developer experience as seamless, hopefully, as building with anything else in the Web3 space. So what are permissions? I've been talking about permissions. So it's kind of a long-winded way of saying that like who can see the encrypted data, right? Like maybe I want another contract to be able to read a certain value. Maybe I want to lease out my information to some sort of like, I don't know, machine learning model or something that's doing training over an encrypted data set and monetize it that way. But essentially, in practice, this is you can kind of think of it as like a modifier, which will check to see that the sender is actually the one that's reviewing this. So if I want to check my own permission, I'm the only one that I want to be able to view what my current balance is for some sort of application. Basically, this permission object gets passed in as a parameter in the function, like passed into the function as an argument. And what it's doing under the hood is that it's kind of checking to see if this permission key, if the key matches the same, if it's the same public key as the one that corresponds to the message.sender, basically kind of making sure that the person that's actually sending this message is the person that has access to the correct key. And so this is another one of the aspects of the Fhenix stack that we try to simplify by using different plugins, such as the Remix plugin, which is, I think, kind of a good way for people that are more visual learners to sort of kind of go through the process and get onboarded that way. But also it can be more complex in the sense if you need multiple contracts to talk to each other. But yeah, so here again is kind of an example of a permission. Basically, sort of like, if you wanted to have an ERC20 balance, where the address would map to a certain integer value, I guess an encrypted integer value of what a specific user would have. But again, you only want to make sure that that's revealed in the right context. And so the implications of like basically a lot of these technologies could be interesting in the form of like solving generalized sequencer issues, whether that pertains to like bundler user ops and like something like account abstraction versus it has to do with like MEV front running, other issues with MEV when it comes to the more financial space. And I think generally speaking, like sequencing is sort of one of the major issues that we're facing. But again, here's like a version of a sample contract. As you can see, it's pretty similar to the last one in the sense where you just really have to import the contract. It's basically one line of code. And then most of the other stuff is basically kind of think of it as like importing a different like integer type versus, so for sometimes there's libraries that let you import a float that you can use. This kind of, instead of a float, you kind of think of it as like it's an import of an encrypted integer. And so this can kind of be used as like sort of like, similar as like you would with like potentially like a database association to build like cascade, like more complex logic with your application on your contract. And so what are kind of the downsides of this? We've been going over, or what are the things to keep in mind in terms of constraint, right? Because basically it seems sort of like the next logical step of using ZK for privacy in terms of it just being more composable, which opens up a lot of options and the ability to actually have the state be encrypted and not having to decrypt. For example, if you wanted to do something similar to like what I kind of said, like the database association system for like, I don't know, some sort of game or a complex application or some sort of like social media, anything, right? Like you basically need to be able to run a query on encrypted space, or else like what are you doing with these numbers? It's always kind of, so like for example, in a lot of standard is kind of like it would have to be decrypted and then the logic would have to be applied that way. Obviously that leaks, so the solution is maybe we bring that off chain. What is the cost of that? What's the cost of security? some could make the argument that that kind of goes against the ethos of what blockchain technology is supposed to stand for. But FHE is still pretty new, and in the sense where like the hardware acceleration, we're still in the pre-ASIC days, and like there's a lot of funding that is going into hardware acceleration specifically. I mean, for me personally, I know I've run into issues where we were trying to work on like a decentralized DEX, for example, not being able to use anything larger than like a 16-bit. Encryption does have its trade-offs. For example, you try to have a fee on a DEX and you can only use 8-bit. How can you can't really get a fee if you're trying to divide by 1,000 because 8-bit only goes up to like 256, right? So these are kind of the design constraints that have to be kept in mind. But for example, even a few months ago, like a division over two cipher, like a cipher, even if you kept the numerator in ciphertext, but the denominator itself even had to be in plain text. And even though those type of divisions, you could maybe pack like 1 in a transaction. Now I think, even in the short period of months, like there has been improvements to figuring out the best way to do these like arithmetic expressions, especially because for now divisions actually is possible. You can have multiple divisions in one specific transaction. But if you want more details and like going over each specific operation, what and how that corresponds to each specific data type, the gas used, how to fit that in a block to prevent overflow, here's the documentation. But anyway, that's the end of the slides. Again, if you want to check out the blind auction, which I think is a pretty good example of using the FHE technology to kind of build something out that could be used, and it's kind of something that we're sort of familiar with. Other than that, also there's caveats to the design that need to be considered. Like I said, we only support up to EU and 32 values right now. So for example, if you wanted to encrypt an address, which was like 25 characters, right, you could turn that each 8-bit into a representation of a byte and then use that sort of to represent a string. So I mean, because essentially if you can create bits, you could create bytes, but these are just like the development caveats that sort of need to be considered, especially when it comes to like the runtime execution, like general tips of performance. But yeah, that's thank you for listening.